Morning.
Good morning, sir.
Morning. Today we are going to discuss about the eigenvalues and eigenvectors. What is the characteristic equation? What is the characteristic equation? Okay. Today we are going to discuss about eigenvalues and eigenvectors of a square matrix. Let us consider A is a n by n square matrix. X is any n by 1 vector or column vector or a matrix. Then there exists a scalar, one scalar lambda, such that the coefficient matrix into a column matrix equal to lambda into a column matrix. This is definitely, it is nothing but one matrix. Multiplication of this matrix is nothing but equating with the multiplication of that column matrix. And in the same way, this is also can be written as Ax equal to lambda x is nothing but Ax equal to lambda into I is I into x, where I is n by n identity matrix. N by n identity matrix. Here in n by n identity matrix, all the principal diagonal elements are ones and the remaining elements are zeros. So there is no change in the given lambda x. Now we want to subtract this one from other. That is a minus lambda I, ax minus lambda I into x equal to 0, the null matrix. O, the null matrix. A minus lambda I into x is common to both. That's why that is nothing but a minus lambda I into x equal to 0 or 0. This is nothing but a 0 matrix or null matrix. Now we want to solve these equations. A minus lambda I into x equal to 0 is equal to O represents homogeneous equations. Homogeneous equations with n unknowns. N unknowns are n variables. So now we want to solve this equation a minus lambda I into x equal to 0 by using system of homogeneous linear equations. If you want to solve this system of homogeneous equations, we come across two types of solutions. One is a trivial solution, another is a non-trivial solution. If this system has a trivial solution only when the coefficient matrix, the determinant of coefficient matrix is equal to 0. That means that a minus lambda I into x equal to O is a given system of homogeneous equations. This is having a trivial solution wherever determinant of this a minus lambda I is a singular matrix. What about a singularity? Singular matrix. Determinant of A is equal to 0, then that matrix is called singular matrix. Based on that, this is a system of homogeneous equations. If this system of equations having a trivial solution only when the trivial solution, that means that all zeros has the solution of given equation, trivial solution. The coefficient matrix A minus lambda I must be singular matrix. This is singular matrix whenever the determinant of that matrix is equal to 0. That is nothing but determinant of A minus lambda I equal to 0 is called the characteristic equation of A, and lambda is called characteristic root or eigenvalue or latent root of coefficient matrix capital A. If you expand this coefficient matrix cap A minus lambda I, determinant of A minus lambda I equal to 0, then we get A minus lambda I, determinant of A minus lambda I equal to some lambda power n plus a1 into lambda power n minus 1 plus a2 into lambda power n minus 2 plus so on plus an minus 1 into lambda plus an equal to 0. That means that if this matrix capital A is a n by n matrix, if you want to find, if you find the equation A minus determinant of A minus lambda I equal to 0, we get the nth order equation polynomial in lambda. If this is a polynomial in lambda, we have to solve this equation for lambda values. We get n values as a roots. Those roots are called eigenvalues. Those roots are called eigenvalues or characteristic roots or latent roots of the given equation. Based on this concept, we have to solve this for each, based on this concept, we have to solve all the this equation by using trial and error method or any substitution method, or by using theory of equations. We have to solve this equation. From that, we get n values, say that are n1, lambda 1, lambda 2, so on, lambda n are eigenvalues. For each and every corresponding eigenvalue, we get the vector. That vector is called eigenvector of the given matrix. Say for example, lambda 1, lambda 2, so on, lambda n having the eigenvectors x1, capital X1 plus capital X1, capital X2, capital X3, so on, capital Xn are the eigenvectors of the given matrix. Now we want to discuss about the procedure to obtain the eigenvalues and the nature of the eigenvalues. First of all, we want to write down the given matrix. Given matrix, check whether the given matrix is a square matrix or not. After that, find the equation. That equation is called characteristic equation, determinant of A minus lambda I equal to 0. Solve this equation for n lambda values. If A is the nth order square matrix, the number of eigenvalues are n or less than n. Less than n is only when with the repeated real roots or complex conjugates as the roots. Complex conjugate as the roots. Suppose if A is a 3 by 3 matrix, two roots are equal, then we have only two roots, only two eigenvalues. So one is the repeated value in that. So this is the way. So first of all, we want to find characteristic equation, that is the determinant of A minus lambda I equal to 0. After that, we want to solve this equation for lambda values. So if A is n by n matrix, then we have n eigenvalues are less than n. This less than n is occurs only when repeated real roots are occurs, or the complex conjugates as the roots of the given equation, as the roots of determinant of A minus lambda I equal to 0. Next, for each and every value of lambda, we have to solve A minus lambda I into x equal to 0 for each and every value of lambda by using system of homogeneous linear equations, which we studied in the earlier chapter or chapter 1. Then only we get the eigenvector or characteristic vector of the given matrix corresponding to that eigenvalue. After that, we have to check whether the given equation is the given eigenvalues are repeated or not. what are the nature, what is the nature of the given eigenvalues, and what is the nature of the eigenvectors. For this, if all the n eigenvalues of lambda are distinct, then there correspond n distinct linearly independent eigenvectors. If all the roots are different values, then we get different vectors as the eigenvectors for that different values of lambda values. Next, in the same way, an eigenvalue of A is repeated twice or more. If any one eigenvalue is repeated in twice or more, there may correspond one or more linearly independent vectors. Thus, the set of vectors may or may not form a set of n linearly independent vectors. This appears only when the repeated roots of the given equation, if the repeated roots occurs in the given equation. Then one of the important concept in this eigenvalues and eigenvectors is algebraic multiplicity and geometric multiplicity. Algebraic multiplicity of an eigenvalue lambda is the order of the eigenvalue as the root of the given characteristic polynomial determinant of a minus lambda I equal to 0. If lambda is a root of given equation 2 times, that means double root, then the algebraic multiplicity is 2. If it occurs 3 times repeatedly, then the algebraic multiplicity is 3. If it occurs 4 times, then the algebraic multiplicity of the given eigenvalue, the respected eigenvalue, is 4. This is the way to explain the algebraic multiplicity of lambda, eigenvalue lambda. Next, we want to describe or discuss about geometric multiplicity of eigenvalue lambda. Geometric multiplicity of eigenvalue lambda is the number of linearly independent eigenvectors corresponds to lambda. If lambda is the eigenvalue of the given characteristic equation or given matrix capital A, the number of linearly independent eigenvectors corresponding to this lambda is equal to the geometric multiplicity. Suppose, for example, corresponding to lambda, we have 2 different vectors. Those are linearly independent vectors corresponding to the same value. Then the geometric multiplicity of this matrix, this lambda, is 2. If it occurs 3 times, 3 different values are the linearly independent vectors, then those are called the geometric multiplicity of the given eigenvalue lambda is 3. So this is the brief discussion about geometric multiplicity, algebraic multiplicity, eigenvalues and eigenvectors. If the repetition is occurs, the number of linearly independent eigenvectors are less than n or n. So this is the way to describe this. Next, we want to solve one problem for eigenvalues and eigenvectors. Look here, or note it down if possible. Find the eigenvalues and eigenvectors of capital A equal to 1.501 minus 0.5, 0.5 minus 0.5, 0.500. This is the given square matrix of order 3 by 3. Of order 3 by 3 or 3. The characteristic equation of the given matrix is determinant of A minus lambda I equal to 0. Determinant of A minus lambda I equal to 0, then the det of the principal diagonal elements are changes only 1.5 minus lambda 0, 1 minus 0.5, 0.5 minus lambda minus 0.5 minus 0.5, 0 minus lambda, that is minus lambda equal to 0. This determinant must be equal to 0. Now we want to expand this determinant by using either first row or last row. We get 1.5 minus lambda into 0.5 minus lambda into minus lambda minus 0.5 into 0 plus 0 minus 0 into anything is 0 plus 1 into 0 minus 0.5 into 0, that is 0 minus of minus 0.5 minus lambda into minus 0.5 equal to 0. Next, simplifying that, we get minus lambda cube plus 2 lambda square minus 1.25 into lambda equal to 0. 1 minus 1.25 equal lambda equal to 0. Now simplifying this equation or multiplying with minus 1, we get lambda cube minus 2 lambda square minus 2 lambda square plus 1.25 into lambda equal to 0. Directly we can say that lambda equal to 0 is the one eigenvalue of this equation because there is no constant coefficient here. So lambda into lambda square minus 2 lambda plus 1.25 equal to 0. Now lambda square minus 2 lambda minus 2 lambda plus 1.25 equal to 0, that is nothing but lambda minus 0.5 whole square equal to 0. Lambda minus 0.5 whole square equal to 0, that is nothing but lambda minus 0.5 equal to 0 2 times. Then lambda equal to 0.5 2 times and 0 as already we have. So the roots or the eigenvalues or the characteristic roots or the eigen latent roots of the given matrix is lambda equal to 0, lambda equal to 1, and lambda equal to 0.5, 0.5, and 1. Now, note these are eigenvalues repeatedly. 0.5, 0.5 are occurs in repeated since there are only two distinct eigenvalues. There are only two eigenvalues, that means that two eigenspaces. But corresponding to lambda equal to 0.5, there should be two eigenvectors that form the basis of the eigenvectors. Suppose let us find x equal to x1, x2, x3 is the eigenspace corresponding to lambda equal to 0.5. Corresponding to lambda equal to 0.5. So if lambda equal to 0.5 from the given matrix A minus lambda I into x equal to O or 0, that is nothing but 1.5 minus lambda 0, 1 minus 0.5 minus 0.5 minus lambda minus 0.5 minus 0.5, 0 minus lambda into x1, x2, x3 equal to column 0 matrix or column vector, that is 0, 0, 0. Now substituting lambda equal to 0.5, because this is occurs in 2 times as a rule, then substituting this value in this matrix, we get 1, 0, 1, minus 0.5, 0, minus 0.5, minus 0.5, 0, minus 0.5. Clearly, in this matrix, we have 2 equal rows. So that means that the rank of this matrix is less than the number of unknowns, less than the number of unknowns, number of variables x1, x2, x3. Here we have 3 variables and the rank of this reduced matrix is only 2. So we have to choose Z in this case. That means that Z, or that means x3 equal to A. x3 equal to some A. Already we have K, or in this way we have to take x3 equal to A. If x3 equal to A, then minus 0.5 into x1, minus 0.5 into x1, and minus 0.5 plus minus 0.5 into A equal to 0. That means that x equal to minus A, x1 equal to minus A. And if you see this matrix, in all the rows of this matrix, there is no x2 coefficients. That means that x2 is also chosen as some other constant value. Say that value is x2 equal to b. That means that all the rows are equal in this case. If you multiply second row and third row with minus 0.15, 1 by minus 0.5, and replacing that, we get 1, 0, 0, 1, 0, 1, 1, 0, 1, 1, 0, 1. So here we doesn't have x2 coefficient in the second row, x3 coefficient in the third row. That's why x3 equal to A, x2 equal to B, then x1 equal to minus C. This is the eigenvector of the given matrix. Next, if x1, x2, x3 equal to minus A, B, A, this can be written as sum of 2 vectors. Say that is A, 0, minus A, plus 0, B, 0. This is nothing but linear combination of 2 vectors. That is nothing but A into, taking A as a common factor from the first vector, A into 1, 0, minus 1, B, 0, 1, 0. So here minus 1, 0, 1, 0, 1, 0 are the eigenvectors. Eigenvectors corresponding to lambda equal to 0.5. If A equal to 1, B equal to 1. If A equal to some other value and B equal to some other value, we come across 2 different eigenvectors. Say that are linearly independent eigenvectors. Linearly independent eigenvectors. Next, we have to find the eigenvectors corresponding to lambda equal to 1. Lambda equal to 1. That is minus, that is substituting lambda equal to 1 in that coefficient matrix, we get 0.5, 0, 1, minus 0.5, minus 0.5, minus 0.5, 0, minus 0.5, 0, minus 1, x1, x2, x3 as a column matrix of unknowns, 0, 0, 0 as a column 0 matrix. Now solving these 2 equations by solving this system of homogeneous linear equations. Here, second row, first row and third row are equals. First row and third row are equals. Then we have to change this 0, 0, 0. And we have only 2 non-zero rows to adding these two, we get 0. This is minus 0.5 and this 0.5 only. After that, we have to solve these equations. We get x1 equal to a, x2 equal to minus 0.5 into a, x3 equal to minus 0.5 into a. So after this, the eigenvalue corresponding to lambda equal to 1 is a minus 0.5 into a minus 0.5 into a. Taking a as a common factor, 1 minus 0.5 into a minus 0.5 minus 0.5. If you take a equal to 1 by 2, we get 2 minus 1 as a eigenvector. If you take minus 1 by 2, a equal to 0, then we get 0 vector. If you take a equal to suppose minus 1, we get minus 1, 0.5, 0.5 as a basis vector of the eigenvalue corresponding to lambda equal to 1. Next, lambda equal to 1. So here we solve this problem by using characteristic equation. Here we have to follow the concept. First of all, we want to write down the equation, the characteristic equation. After that, solve that characteristic equation for lambda values. Then only we get eigenvalues. After getting eigenvalues, we want to solve this homogeneous system of equations for each and every eigenvalue corresponding to each and every eigenvalue. We get different or linearly independent eigenvectors. This is the procedure to find eigenvalues and eigenvectors of any matrix. Suppose here a equal to 6, 0, 0, 0, 7, 3, 0, 0, 9, 5, 7.50, 2, 6, 0, minus 7.5. Can you name it? Anyone can name the given matrix A? Anyone can name the given matrix capital A? Anyone can tell me the name of the given matrix? What is the specific name is there for this given matrix? What is this? Vinila?
Sir, 4 by 4 matrix, sir.
4 by 4 matrix, then?
Upper lower triangular matrix, sir.
All the entries above the principal diagonal are zeros.
Zero, sir.
That's why this matrix is called
Lower triangular matrix, sir.
Lower triangular matrix. Okay. So now we want to check whether the given matrix is a lower triangular matrix. What about the eigenvalues of this lower triangular matrix? Since the matrix capital A is a lower triangular matrix, the eigenvalues of capital A are the diagonal elements of A. Since we have to write down the characteristic equation of this equation, 6 minus lambda 0, 0, 0, 7, 3 minus lambda 0, 0, 0, 9, 5, 7.5 minus lambda 0, 2, 6, 0 minus 7.2 minus lambda equal to 0 is the characteristic equation. If you expanding this matrix, this characteristic equation by using first row, we get only 6 minus 6.5, 6 minus lambda into remaining principal diagonal values that are 6 minus lambda into 3 minus lambda into 7.5 minus lambda into minus 7.2 minus lambda equal to 0. If you solve that equation, we get lambda 1 equal to 2, lambda 2 equal to 3, lambda 3 equal to 7.5, lambda 4 equal to minus 7.2. So from this, we have to observe that the lower triangular matrix has the eigenvalues of lower triangular matrix are the principal diagonal elements. In the same way, if this is an upper triangular matrix, if this is an upper triangular matrix, that means that if these all non-zero entities below the principal diagonal is transposing into upward values, we get a upper triangular matrix. In that also we have to expanding that by using first column, we have to get the same values. That means that we have to make a conclusion from these two matrices. The lower and upper triangular matrix are a triangular matrix as the eigenvalues as its principal diagonal elements, as its principal diagonal elements only. Okay, are you follow? Are you follow the concept?
Yes, sir.
Okay.
Yes, sir.
Okay. Suppose here we want to this is the given matrix. Capital A equal to 2 minus 3.5, 6, 3.5, 5, 2, 8, 1, 8.5. This is the given matrix capital A. Now we want to change this as A transpose. The transpose of this matrix capital A is, the transpose of this matrix capital A is 2 minus 3.5, 6, 3.5, 5, 2, 8 as a column value, 8, 1, 8.5. If you observe these two matrices capital A and capital B, is there any similarity in the entries? Is there any similarity in this entries of this matrix? Here in this matrix, capital A and capital B, the values are not changed. One value, some values are not changed. The values are not changed in principal diagonal elements, right?